Hey Rana, Jay here.
Yes, like Jay is our head of applied AI. He's been with Affectiva for over 5 years now, and he runs our science team responsible for building our different emotion classifiers. Over to you, Jay.
Great. Without further ado, again, let me introduce myself. My name is Jay Turcot. I'm the Director of Applied AI here at Affectiva. That is a fun and lofty title to say that I head the research team. So as Rana mentioned, I've been with Affectiva for over 5 years, working on the core technology. So we're the team tasked with taking the input video that we see and converting that into the usable metrics, building the underlying models, training the models, and packaging that up for deployment into our cloud-based services or into our SDK. So today's talk, what I wanted to do was just talk a little bit about the metrics that we have here at Affectiva, and give a brief glimpse into sort of how the software works. Now, for those who are computer science graduate students in computer vision machine learning, I'm not going to be digging under the covers that much. This is going to be coming more from the point of view of someone who wants to use our SDK, who just wants to get a little bit of intuition in how this SDK actually does it. How does it go from pixels coming out of a camera into these measures in a frame by frame? And so that's going to be the main center of this talk. So in the outline, first briefly describe why the face and describe FACS, the facial action coding system, because that's actually a very important part of the philosophy here on the Affectiva research team. Do a quick overview of how the technology works and describe sort of the metrics, showcase the metrics and emotions. Give one quick example of how it's been used in the market research world to date, and then go back and dig a bit deeper into the specific steps of the technology, the computer vision pipeline, and maybe share a bit of insight or the implications on how this might explain the behavior you might see coming out of the SDK. If there's time, we'll do a little bit on still images versus video, and sensitivity to pose and luminance, the head orientation. So this track is going to be really quick, and I apologize for that, but we'll be recording it so you could circle back. So why the face? Well, there's a couple of motivations. When Affectiva started out, we wanted to be emotion sensing technology using a multitude of inputs. We even manufactured a physical sensor to measure galvanic skin response. But we decided to focus on the face because, one, the reactions on the face you get are spontaneous. They happen in real time, so you get real-time feedback, and really importantly, the sensor is extremely unobtrusive. It requires only a front-facing camera, and if you think about what technology has front-facing cameras, you've got your smartphones, you've got laptops. An RGB camera is a very, very cheap sensor to enable such a great signal. Now, this great signal from the face is because the face transmits rich information. It transmits ideas or concepts like your emotional state, the happy, sad. In interactions with one another, we look, face-to-face conversations that being able to read each other's faces are what help us read these nonverbal cues, and that's what we strive to do with our technology. We also get measures of intensity. Is it subtle? Is it intense? And one great thing about the face compared to other biometric measures like heart rate, EEG, brainwave activity, is that really what it is, this technology is quantifying what you would see. It's like encoding what you get if you're standing behind a one-way mirror. So the fact that someone frowned, it still just remains that this person frowned, and you as a human being can interpret, you as a developer can interpret, why would my user base, why would one of my users be frowning right here? To study the face, you really have to go back to, or one of the roots of what we believe is something called the facial action coding system. This was developed in 1978. It was published by Ekman, a psychology researcher studying human facial expressions. And what the facial action coding system was a system to help codify the expressions that we see. He called these individual facial movements action units. What they are they're independent movements of the face, almost mapped one-to-one with the muscles of the face, and it allowed researchers to finally describe what they were seeing on the face in an objective fashion. So the action units, there's I think over 20. It's been extended to include eye movement, head movement, etc. But The facial movements are given numeric codes as well as an intensity scale of A to E, E being the most intense. So for example, an AU1, a 1 is an inner eyebrow raise, often associated with sadness, or an AU9 is a nose wrinkle, the muscle that contracts, pulling the nose up and the brows down right between the eyes. And so now researchers could actually look at and run studies analyzing facial expressions. So as an example, here's this face. In common language, call it the not bad meme, you know, the Obama rage face. You might call this expression a frown. Well, that turns out frown is actually ambiguous because that's a North American thing only, where the frown is a mouth expression. Turn that frown the other way around. If you go to Europe, if you go to the UK, a frown is actually a brow lower. That furrowing of the brow is what they'll call a frown. That might be shifting with the younger generation as the prominence of the frown emoji, being this sad face, becomes more prevalent. But it just goes to show that human language isn't actually necessarily that great for describing expressions. In fact, this would be a 15E and a 17E. So a lip corner depressor, the corners of his mouth dropping, and a chin raiser, the chin coming up just to make this telltale expression. Now this lets us describe very specifically what's going on in his face and breaks it down into the two contributing components that then combine to make this facial expression. Now, why is FACS important? Well, it feeds into how the technology works. So a quick overview of the technology. When it receives a still image or it receives a frame of video, under the hood, there's a number of computer vision algorithms. First we locate the face and identify landmarks on the face. Then our machine learning algorithms, and I'll go into this a little bit more, analyzes the texture, the pixel information around the face to identify these individual facial expressions, these individual actions. And then later, these combinations, individual facial expressions, we currently detect 20 of them, can be combined into hundreds of different combinations to manifest all the different expressions you see on the face. In reality, the human face only expresses a subset of those. So currently, the SDK, what it does is it reports back some of our metrics, include the individual action units. So we've got the individual facial expressions occur. In total, the SDK reports 20 of these, 15 are shown here. And then these individual combinations, the specific combinations of expressions are then also represented as the 6 basic emotions, as well as higher level summaries of what is occurring on the face in the form of valence, which is a measure of how positive or negative is the expression, engagement, which is on a scale of neutral to a very expressive, how expressive is the face. But keeping in mind that the ability to detect these individual movements manifest in other ways, we also map them to the closest emoji, where again, saying someone smiles is only so descriptive, whereas it turns out you can have a very big smile, a smile with your lips parting or your eyes closed. The technology, the individual metrics have the ability to detect these different combinations, so we map them into emoji. As well, we also, from the face, detect appearance metrics. We estimate the age, the gender, the ethnicity, and can also tell whether or not people are wearing glasses. Now, these are all just done based on the visual appearance of the face. So as I alluded to, what drives all of this, the core technology here is called computer vision and machine learning. There was a question in the earlier track asking about, what deep learning approaches do you use? I won't be going into that in detail now, but that's deep learning is an area of computer vision that Affectiva is focusing on intensely, and all of the subcomponents I'm going to describe, we're looking at deep learning-based approaches to see if that pushes up the accuracy. I've written a little bit about this on our blog, and we'll hope to be putting out more blog posts on this as well as publications. So check out our blog at blog.affectiva.com. So how are these metrics used? One way is that we can trigger events based on facial expression. So again, you're in an app and you see someone smile. What might you want to do when you notice that a person smiles? In a social robot, that could feed a learning feedback reinforcement learning algorithm to say, hey, robot, whatever it is you just did, that was good. So it could be part of the feedback loop there. In some of our research work we've done, we've built predictive models based on individual responses where again, we analyze people's responses, but also gather direct feedback in the form of a survey, and we estimate how much, without that intrusive survey, how much can we actually just predict what it is they were going to do. Now, that survey could actually be any kind of outcome. It could be that they purchased, it could be that they quit, but ultimately, you can look at, are there any clues in their behavior within the app, but also in their reaction to the app that drive more accurate predictions. You could also do analytics over time or analytics across individuals. In the market research world, one thing we use this technology for is to look at people's spontaneous reactions to video content. And rather than look at just a single individual, like observing a focus group behind a one-way mirror, we look at hundreds of individuals and we actually aggregate all of their responses. So what you get is effectively interest expressions. You should tell, you know what, at this point, 30% of the women were frowning, but none of the men were. What happened in this? And this becomes an invaluable tool because it's like a one-way mirror onto a focus group, except you can look at hundreds to thousands of faces at the same time. Now imagine this aggregated in your app, screen by screen, split by demographic, or if you don't have that directly, our estimate of the demographic. It does provide a very powerful analytic tool. With a little bit of time left, what I want to do is dig a little bit deeper into the core technologies, like that computer vision I mentioned. Well, what are the different technologies that exist? The first step in this pipeline, you have an image that appears. You have to first tell, is there a face there? And that's a problem called face detection. Smartphones do this. Your Nikon camera's been able to do this. But it's basically the initial detection of a face. It tells you the position and the scale of the face, roughly where the face is. Now, in the SDK, what are the considerations for the SDK? Well, currently, and we're working on improving this right now, actually, the face needs to be near frontal, call it 10 degrees upright and 15 degrees forward for us to be able to first detect it. Also, looking for faces in this potentially high-def image can be an expensive proposition. It can be time-consuming, and that's proportional to how far you have to search. So looking for very, very, very small faces versus looking for only constraining your search to look for large ones can change the runtime performance. And that's why in the SDK, there's actually two modes. If you know you're using a front-facing camera and this is direct interaction, we don't need to look for that really, really tiny face. So let's save that CPU time. In the multi-face scenario where you expect more than one person present, this face detection needs to occur constantly in the background on a periodic pulse in order for you to be able to acquire and scan for new faces. Again, once we hit the maximum number of faces, I believe it's a parameter in our SDK, we stop scanning for new faces until there's room in the processing pipeline for more. Once we've localized the face, we then once we've detected the face, we then localize the landmarks and track them. So our current landmark detector and tracker tracks 34 points around the face. Now, these 34 points are used in two ways. One, it gives us an idea of where the mouth is, where the nose is, where the eyes are in fine detail, but also it lets us, these 2D positions, lets us fit a 3D model to give us an estimate of the orientation of the face. One interesting thing about the landmark detection is once we've locked on with our tracker, we can actually follow the face through a much wider range of positions, scales, orientations. We can follow the face to, about 30 degrees frontal. And again, we're revving our tracker now to improve the range of that. We also could follow the face completely upside down. One thing to note is that sudden position changes of the face can disrupt tracking. So on a frame-by-frame basis, we check how well are we doing? Are we still locked on to the face? And if we notice it performed very poorly, we'll cut out the tracking. So that's when you'll lose the face. This could be something covers the face up, they put a hand in front of their face, and we'll lose it until we reacquire it. Or it could be that they turned away and we, again, are no longer confident that we're tracking a face. Things like sudden movement with a really, really low frame rate could also do it, but mostly it's going to be, occlusions, things blocking the face, them turning away. Once we've acquired the face, we detect the individual expression. This is a suite of individual classifiers. They look for the presence of each of these individual expressions, and this analysis is done on a frame-by-frame basis. So the analysis relies on visual texture. So it looks for shading, it looks for wrinkling. It doesn't look at the specific landmark positions per se. It actually looks at all the fine-grained texture around it. And what that lets you do is pick up more nuanced expressions that aren't necessarily going to move those landmarks. Brow furrow could be a very subtle brow furrow, but you'll see a telltale wrinkle between the eyes. Now, this detection, the robustness is gained through machine learning, through observing thousands of real-world examples in a variety of conditions, a variety of faces, a variety of intensities. And again, refer back to the blog post on our Affectiva website. And then finally, we do the expression interpretation. So this is a layer on top of the individual expressions that describe what's occurring on the face, that then provide a high-level interpretation. We do the basic 6 emotions, which are a set of emotions well studied in psychology literature, as well as contempt. Again, we have a positive, negative score of valence and an overall intensity score of engagement, and we also map them to emoji. Now, in the SDK, these interpretations are available again on a frame-by-frame basis, and they're really just a transcoding of those 20 individual facial movements into an easier-to-consume package. So it's a great starting point for analysis. But remember that you can always drill down into the underlying expressions. That again, your human intuition is still valid. Now, a few more notes. We've got 5 minutes left, which was originally geared for questions, but I can wrap up quickly. On the subtlety of video versus images, human facial expression detection is actually quite challenging. In fact, coding, you actually, to code a still image, you require a baseline, a reference, which is their neutral face. For example, the top 2 images here, on the left, we've got a really subtle inner eyebrow raise, and on the right, we've got a really subtle frown, turning the lip corners down. Now, in that right image, would you be able to tell that there was an expression there without this lower image, which is the reference? Most likely not. Some might. Or the wrinklings on his brow, is that just natural wrinkling, or is that, again, a sign of an inner eyebrow raise? So what this means that in the video case where we could build an estimate of what we believe the person's neutral face is, and that lets us account for person-specific appearance. Are they like the Joker from Batman, where there's just a permanent smile on their face? Again, this overall improves accuracy, improves sensitivity. Because of the reach, our desire for reaching this technology, we don't require an explicit calibration, but in the video, we do try and build an estimate of what their neutral face is. With a still image, no additional information is available, so you are going to get a different result. And it will be a little bit more sensitive towards, things like wrinkling due to age, etc., but it's still quite accurate. So the take home here for the SDK users is if you are tracking a single individual over multiple frames because it's the video, definitely prefer the video-based SDK. You'll benefit from speed ups in tracking, and you'll actually benefit in terms of the accuracy of the output as well. And one final note here is on environmental lighting conditions, pose, luminance. So our metrics are very robust to lighting. But what I want to say is this is the lighting of the face and not the lighting of the room. You could be in a bright sunny day, but extremely backlit, and the face will be very dark if you've got the camera pointed up at the sun. But that being said, what the technology sees is the underlying pixel information, and that actually inherently built in has contrast normalization. It can see things on the face that is even hard for the human eye to pick up without you adjusting the image. Pose is something that's a bit more challenging for expression. So right now, the technology is still somewhat constrained in that we only work around 25 degrees frontal. So people sometimes think, oh, can this technology work from a surveillance application? I've got a camera mounted in the corner of the store. The current version of the SDK doesn't, in part due to the data we have available. Again, that's probably one of our next pushes on the improvement, is to increase the range of these classifiers. Right now, we look at around 25 to 30 degrees frontal, I think the exact cutoff, but from our testing and evaluation, we don't have enough data to be confident that we're reporting back accurate data. So what you'll notice is in some cases, when they start to turn really far away non-frontal, we won't report metrics back, but we'll still track the face. And that's because while we are still generating these metrics, we're no longer sure from the evaluation data that we've got on hand that we're confident in what they're outputting. So we suppress the output of the individual metrics there, but allow the tracker to continue to track that face for when they turn back to face the camera. And as always, we're expecting improvements of these in future releases of the SDK as we improve these classifiers, learning from more and more data. So with that, I'm stopping just on time, but I'll stick around probably an extra 5 minutes to cover some questions. So thank you very much all for listening in. I'll turn it now to some questions from the audience. I'll just go through these as they come in. I've got a question from Bhavit Desai. If a person has a lazy eye does the SDK take that into account, or how would it affect the expression detection? So that's a good question. One of the expressions is the lids lowering, the eyes closing. So all of the expression detection, accounting for the person individual variation, accounts for some amount of variation, but up to a limit. For example, if the lazy eye resulted in the eyes being closed, the technology would still say that the eyes are closed. If they show up though and their eyes are permanently droopy, I think it depends on the magnitude of how far that is. So for example, if someone's putting, like, we're seeing intense expression on a person's face, no amount of correction will do that. And how we determine that amount is based on the data we observe. Unfortunately, I don't have much lazy eye data to compare, but ultimately, I think that should give you the intuition on how it works under the hood. So do we have similar graphs of accuracies with diverse illuminations of the face? Yes, we do. Maybe I'll see if I could put that out somewhere. We have, internally, we generate these graphs for a bunch of different conditions. The overall luminance of the face, how cross-lit the face is, how blurry the image is, et cetera. And we look at the accuracy as a function of these. What we've seen is that unless the image is really dark, and I think these are guidelines that we share on our developer page. For example, on the brightness to darkness scale, I think, yeah, an average of 35 on a scale of 0 to 255 on the face is how dark it has to be before we start seeing a really material impact in the expression detection performance. Please give us the percentages of predictions in different situations, the worst and the best predictions. I assume this is with regards to the accuracy. The accuracy measure that we use is area under an ROC curve. So some of the really, really rare expressions you'll see in the low 80s in the area under an ROC curve. And some of the really good expressions you'll see, really high 90s. And how to determine where something fits, the really common expressions, eyebrow furrow, eyebrow raise, smiling, lip corner, like frowning, those are sort of larger expressions, more commonly occurring. So the algorithms are more robust to those, whereas some of the really subtle expressions that we see less common, pressing of lips, for example, those will be on the lower side of things. One question here is, how is the biggest database of emotions helping make the algorithms of emotional detection better? In our data set, we've got over 4 million, approaching 5 million videos of people in real world conditions, in natural lighting, et cetera. So when it comes time for us to improve one of our classifiers, what we could do is mine that data set, look at how we've analyzed the technology, and look for additional examples of individuals. So again, to build robustness across a variety of individuals. We also look at cases where the classifier is somewhat uncertain, and again, we have human annotators annotate those to give us the correct response. So that feeds the overall training pool. Another way that in machine learning, at least, people look at exploring is techniques called semi-supervised, unsupervised learning. Again, in modeling the sensitivity to head motion, the reaction of these classifiers to head motion, you could first observe in all the 4 million videos how these individual expressions correlate to first pre-train an algorithm and then fine-tune it with the actual annotated data. But in machine learning, the gold standard is still through annotated data, and what we have is a vast pool of data in real-world conditions to actually train models from. And models benefit from representative real data. So you train a model, we try to train a model with purely academic perfect illumination data and try it in the real world, and it does not do well. But train an algorithm based on real world data and apply it to the perfect conditions, and it does just fine. What if there's more than one person in the video feed? So the SDK does cover multi-face, so the face detector, if it detects multiple faces, will return it. If you set yourself to only look at one face, it prefers the largest face present. So for example, if it detects 2 faces and there's only one face present, or you set the maximum number of faces to track, it'll pick the largest face. If you set it 2 or 3, in the individual SDK talks, you'll see there's a dictionary indexed by a face ID of all the faces present. What are the algorithms in different can you give us the accuracy of the algorithms in different situations? This is always a really, really tough one to answer, and I'll be upfront. It's not me trying to dodge the question. The accuracy that we use, again, is an ROC, the area under our ROC curve. Where accuracy becomes really tough is that the accuracy of an algorithm is entirely dependent on the test set. So in computer vision, for example, there's a hand digit recognition data set called MNIST, and the accuracies out of the report are 99% accurate, because at this point it's a solved problem. It's an easy problem. Our data that we evaluate on are subtle expressions. So in the facts coding, call it the A, B, C intensity, really subtle expressions, and also have terrible illumination. We haven't constrained the movement of the individual or the pose of the individual, so it's a really challenging case compared to a really clean data set. So I think one thing we'll look at is probably find one of the standard facial expression data sets that are studied in academia, where you see a lot of the published reporting, and just put out accuracy numbers on that. But internally, what we are driven by are the accuracy numbers on a real-world test set. And let me see here, more than one person, measure samples frame by frames, great. And then here, maybe I missed it, are the emotion samples based frame by frame, or does it analyze changes in the expression over time? That's a great question, Colton. So right now, the emotion layer is just the interpretation of that still image, that frame by frame. The modeling of it, or the longer term modeling over time, is something that we're starting to explore, exploring the dynamics of it. But in the current version of the SDK, what it gives you is just an alternate interpretation, or an interpretation of the expression it's seeing in that still frame. And then one question, how do our algorithms improve human emotional intelligence? Well, I would actually say that our algorithms, the reason we built these algorithms, or originally these algorithms were built as an enabling technology to help people with autism. So as an assistive technology, there's one startup called BrainPower that we've helped them build the SDK and get it running on Google Glass. And again, this is for people that don't necessarily pick up the facial expression cues as well as others, because reading and interpreting facial expressions is a skill, and there's varying degrees of skill involved in that task. So in some cases there, we're hoping that it could be an assistive technology. Where I really see this technology being useful is to help human-machine interaction. So again, to give machines the signal, they need it numerically. All learning algorithms, all AI algorithms need it in a numeric fashion, but to give them this quantified information that previously was unavailable. So there, I think it's really going to help human-machine interaction. But really, it comes up to the individual use case. What can individual developers do with it? I imagine in a video conference, me broadcasting to the crowd, I have no sense of audience reaction. I know there's a large number of people tuned in here, but I have no sense of being able to read the crowd the way I would standing in front of an auditorium and being able to read individual faces. So again, being able to have that quantified shown to me without having to scan the crowd is another way. But ultimately, how does this improve human emotional intelligence? I think it's just bringing this emotional signal front and center into our technological world. And I actually leave it to all the developers tuning in today to attend the upcoming talks in their platform of choice, think up cool ideas of how they could use this technology, how they could drive and change the human-machine, human-app, human-to-human experience with this new signal. And yeah, I'm really excited to see what people do with this technology. And that was the underlying motivation behind releasing the SDK and putting it in developers' hands and having a developer day like today. So with that, I've actually run 10 minutes over, and we'll cut it short. Thank you very much for attending. Thank you for all your questions, and I hope you have fun at the rest of the talks. There'll be a number of talks going platform by platform, and I believe they'll be going through code walkthroughs, showcasing the individual developers. You can see some code and get started from there. Thank you very much.